Good afternoon, everyone. Welcome to the resctrl Microconference. My name is Fenghua Yu from NVIDIA. So today we are going to have 5 topics about risk control from Renee, Tony, Babu, James, and me. Because we only have 45 minutes and 5 topics, so each one only 9 minutes. But after this slot, we have a coffee break, 30 minutes. Hopefully we can still take some time over there. Okay, having said that, first the speaker is Renee to talk about the risk control schema descriptions. Renee, could you please take over the control?
Hello, my name is Reinette Chatra, and I am here to raise awareness about some planned enhancements to how user space manages resource allocations via the schemata file. First, just to start, nothing of this is final. You can find the current discussions in the email threads. The latest one there starts with a great summary written by Dave Martin. There's an echo that I have. Okay. For the other information for previous issues and side discussions about opens, you can find that in the other threads there. So I would focus on memory bandwidth resource allocation, but everything is intended to apply to all resources. The reason is because of new features coming to memory bandwidth allocation. There are 2. So the first is to support new control values. The first one, the upcoming hardware can support memory bandwidth allocation at finer granularity than what the default allocation of percentage base allows. So some of the hardware can look like a range from 1 to 511, for example, and where 1 is bandwidth allocation and 511 means all the memory bandwidth. And on some hardware, the memory bandwidth allocation may be expressed in fixed point fractions, where the fraction number of bits for the fraction is discovered from the hardware. So in addition to new control values for existing memory bandwidth allocation, we also need to support multiple controls for a resource. So for memory bandwidth allocation, we have in addition to memory bandwidth allocation, hardware also support minimum and maximum bandwidth limits to support use cases. How the current proposal looks is to support that by separating resources from controls. So when a user goes to the info directory, the user will find the regular resource there and a new directory, for example, resource schemata. And in this resource schemata directory, there would be subdirectories named for the controls. The prefix would be the resource name, and then the suffix would indicate the new control. User can then find the properties of each control inside these subdirectories. User is expected to start with a file named type that would describe the type, and it would be backed by some documentation that describes what files the user can expect to find in that directory and what the properties would then mean. So as an example there, how it may look for the existing memory bandwidth allocation is user can know that writing a control value C must be between the values found in the minimum and maximum files. And then the actual resource allocation written to the hardware is expressed in a formula there. Now, of course, we have to remain backward compatible. We cannot just use the control values for the existing memory bandwidth allocation schema, and we cannot just take it away. So the current idea is to introduce a new schema, a new control. In this example, it is shown to have been named optimal. So we have the legacy memory bandwidth control schema, and the new one that can support the finite number allocations. The consequence of that is that there are two resctrl controls, and then they're both backed by a single hardware control. So a user may see when writing to this legacy control and then reading back the information, it would be reflected by both of these controls. This relationship between controls is not obvious by looking at this schematic file. And the current idea is to express it via the file hierarchy inside the info directory, where the directory the subdirectory would indicate the control, and then the parent directory would indicate that it's an abstraction. So on the left is one example. Of not all hardware supports all controls. So this hierarchy may look different on different hardware. The middle one shows the hardware that only supports minimum and maximum. And then there would be an abstraction of the finer granular memory bandwidth allocation, and then the additional abstraction for the legacy allocation. There could be additional thank you. There would be additional abstractions available. So if rest control wants to have some semblance of consistency to user space, then it may have additional abstractions as shown in the right there. Now, this where user space can see multiple controls that are backed by a single control on the hardware. One potential problem may be depending on how user space interacts with the schemata file. So ideally, user space would only write changes to the schemata file. But if user space, for example, reads the entire schemata file, just modifies the parts that it understands, then it would see different behavior. So hopefully user space like this does not exist. If they do, please let us know. We have some ideas how to solve it that are under discussion. And finally, the backward compatibility with region aware is not clear yet. There may be, instead of a general memory bandwidth allocation, the user may be able to allocate memory bandwidth to different regions. Having the legacy apply to all regions seems reasonable, but if the user modifies one of the region's memory bandwidth, it's not clear how to reflect that in the legacy schema. I understand this was really fast. If anything sounds of interest to users or vendors, please join us. We'd like to get this right. Thank you.
So I'm Tony Luck. I've been working on res control from the very beginning of res control. And today I'm going to go through a little bit of the details of how region aware works on the Intel systems that are upcoming shortly. Renette already gave you a few hints about this, but I guess it's more going to be background to what Renette was just talking about. So what is a region? The system at physical address space is divided by memory type and topology into ranges, and each range is tagged with 2 region numbers. One region number is for access by CPUs local to the range, and the other one is for remote access from CPUs elsewhere in the system. And one example is that, typically the range from 0 to 2 gigabytes is DDR on the first socket. So that range would be tagged with, or could be tagged with 0 for access from node 0, but it will also be tagged with 1 for the remote access from CPUs on other nodes on the system. And that will go through the whole rest of the physical address space. So you might have some CXL memory that could be tagged with region 2 and 3, depending on whether it's local to a particular node or remote from a node. Right now, in the first implementation, there's only going to be 4 regions. There can be quite a lot of ranges, though, so we should be able to describe quite a few systems, but we will not be able to do things like if you have a system that has more than 2 sockets, you won't be able to individually set up regions for access from different sockets in different regions. You'll just have a concept of my local socket and all the other sockets are remote. And this is all going to be set up by the BIOS. The OS gets to live with what the BIOS set up for the region mappings. It's described in an ACPI table, the MRRM table. The patches for that are already upstream, and the values of this all appear in sys firmware ACPI regions. So yeah, here's our example. What we're expecting is that local DDR will be region 0, remote DDR 1, local CXL 2, and remote CXL 3. And if you don't have any CXL, then you won't have a region 2 and 3. And these ranges don't necessarily have to be populated memory at the time that the firmware runs. So CXL hot plug is under control of the OS. But the physical address ranges that you can map your CXL memory are all reserved by the BIOS and described in some CEDT tables. So those ranges may be empty initially, and then you map in some CXL memory with a hot plug operation. Memory bandwidth monitoring changes a little bit. We have, as before, there are separate counters for each instance of an L3 cache, but instead of having a local and a total counter, there are counters for each region. So you'll effectively be able to count access to your local region or to your local DDR, to your remote DDR, your local CXL, remote CXL. As Renette was discussing just now, we're not wedded to particular names for the events that you'll show up, but potentially it might look something like this, where we have an MBM local bytes, which is fairly compatible with what we have today, and then MBM remote and SMBM local, borrowing a little bit from the AMD idea of calling the CXL memory slow memory, and then SMBM remote for CXL on remote devices. Again, sort of that's up for discussion as to exactly what we'll end up calling those. And again, Renette stole some of the thunder for this with the updated bits of discussions of what's been going on the mailing list. There'll be entries in the schemata file for each of the different regions, and as Renette just described, info files to describe some of the additional capabilities that we have. For instance, finer grain than single %, and these minimum and maximum controls that allow you to specify, for instance, for some high priority processes, you might set a minimum bandwidth to say, hardware, please do not throttle this below this level. But you can also, on low priority processes, set some maximum bandwidth to say, do not let these processes go above a particular level. The hardware will monitor how stressed the memory subsystem is and allow things to vary around from the optimum value that you set between those minimum and maximum ranges. So when the system is distressed, the low priority processes may be all shrunk down to those minimum bandwidths, and the high priority processes were allowed to keep getting the bandwidth that they want, so long as the system can still maintain the levels that you configured. And all of this is described in a public document, the RDT architecture specification. It's currently at version 1.2 at this URL. Somewhere before the end of this year or maybe early in January, the 1.3 version will come out with a few extra wrinkles in, but the basics that I just described are all in the 1.2 version. And if there are questions, I can take them, or we can pass on to the next presenter.
So I was talking to you, Chen, and this goes back to the naming. Like, we have a pretty complicated SysFS topology for describing the HMAT, and that's all in terms of nodes. We don't try to do local, we don't try to do remote, we don't try to do CXL or slow or these type names, because they're always going to be wrong. Because your CXL can be fast and your DDR can be slow. Like there is no, it's just ranges with performance. So what would break, or what do you think about just doing this in terms of nodes? Yes, there may be a node that has multiple types. That's firmware's problem to solve, but otherwise a node just kind of naturally fits with a lot of other interfaces that we have.
Well, a lot depends on where you want people, or how many steps you want people to go for the work. I mean, I think we've been trying to look to ways that the schemata file will be fairly descriptive without having to then go to other resources. Although, we're probably going to fail to some degree on that you'll have to go to the info file to understand a bit about what info directory to look up what some of those things mean. Our original thoughts on this was just to actually call it region 0, region 1, region 2, region 3, which is just a very generic thing, and make everybody do the work to say, what is my region 0? Oh, I'll have to go look in sys firmware ACPI regions to find out what my regions mean. And even there, it'll only tell me what node they belong to and what address ranges they are. And then they have to go and look at the HMAT table to say, oh, this address range in the HMAT table looks like it's pretty fast, so maybe it's DDR, or it looks like it's got very long access time, so maybe it's CXL. I don't know there's really a very good answer to this. I mean, we would like to have something that is not super system specific, so that if you're on an Intel system or an AMD system or an ARM system, you'll have similar kind of setups to be able to, so you don't have to rewrite all your upper level software to say, oh, I'm on an Intel system, it looks like this, or I'm on a ARM system, it's completely different. I have to have a completely different set of management tools to go and work it. So the discussion's open on exactly what we'll call things. If we can come up with something that makes everybody happy, I'll be very surprised. If we can come up with something that everyone can live with, that'll be nice.
Tony, as you were describing kind of that walkthrough and this desire to have this work everywhere, it kind of sounded like you were supporting Dan's idea, because nodes sounds like the thing we all have in common.
We do, but the Intel hardware doesn't quite support nodes. As I was saying, we're not going to have enough regions to be able to describe bandwidth in all the different traffic between different nodes. Regions are quite expensive in hardware because you have to have counters for every RMID within every region. So if you say, hey, we want 8 regions instead of 4 regions to describe this system, then suddenly you have a massive number of extra counters available, because you need hundreds of counters per region because you have hundreds of RMIDs. Yeah, we're ultimately going to have to compromise a little bit on what we would like to have and what we can actually support in hardware. If there was a question I didn't hear in the static.
We're out of time. We have to move to the next talker or next presenter.
This is Mugar here. I work for AMD, and I'm going to talk about a few features which are coming in AMD systems. So I'm working on that right now. So I'll talk about that. Okay, so key enhancements for the next. So we have added ABMC support, that's Assignable Bandwidth Monitoring, okay, or MBM event we call in resource control. So we have increased number of counters from 32, it was from the original, the first generation where it supported. So we moved to 64, and there is no change for that. So it's already taken care with CPID automatically detects it. And then there is we call global memory bandwidth allocation. So it's MBA, and it is basically extension to MBA called global MBA. And then there is a privilege level 0 association. So I'll talk about that. So as you guys know, AMD has we have a multiple CCX and CCD architecture. So if you have to, MBA feature enables users to set bandwidth limits individually on each domain. So each domain is either CCX or CCD here. So this can cause problems because in a system where application runs on multiple domains, we really cannot control how much bandwidth it's going to use, because normally if it runs on both, it's if you need two domain system, if it runs on both the two domains, so it will be addition of limits on both the domains. So it can use that. If application runs just the one domain, then it will be the limit for that domain. So it can lead to under-utilization and over-utilization some cases. So we needed to have a control over that. So we have added GMBA support for that. Basically, it provides option to set the ceiling for group of domains. Basically, you select which domains you want to run the application and make them as we call it them as a GMBA control domain, and just set the limit for that. In that case, what happens? So if it runs on one domain, maximum it can use is the limit for the GMBA control domain. If it runs on both the two domains, also it will run with the same limit. So it cannot exceed GMBA control domain limit. So the changes are actually straightforward here. Basically, we'll have to add a new resource, GMBA. I call it as GMBA, and there's a mistake here, GSMBA. Basically, the same thing applies to CXL also. So we'll have two new resources type added, and there is an example I have given here. In this case, the domain 0 and domain 2 are combined together and made as a GMBA control domain. So the other domain, the limit doesn't apply to the other domains here. It just it basically overrides MBA limit. It takes GMBA limit applies here. Privilege level 0 association. This is another problem we have seen in. I think it is probably generic for all the vendors. So if a class is aggressively throttled and it moves to kernel mode, the kernel operations are also aggressively throttled. So basically, we don't have a separate that kernel as user mode limits, we cannot separate that. So it's both the limit set for a class will apply user level as well as the kernel level, kernel mode. This can lead to performance bottlenecks and hinder forward progress and cause delays in system under heavy system load. So for this we have added a new feature, privilege level 0 association. Basically, it allows user to specify a class and RM. Either you can class RMID with the execution level 0, and you set the limits for that class. So when enabled on a hardware thread, when the thread enters privilege level 0, transactions associated with that will be automatically associated. I mean, it will basically the limits for that thread will be use PLGA class or RMID. So we call it as PLGA class or PLGA RMID. Otherwise, hardware tool, if that is not the feature is not enabled, then basically hardware thread will be associated with the class and RMID identified by a PQR association register. We call it as PLGA PQR association register for this feature. So we can basically, what feature does is it gives an option to user to change the limits on user mode and kernel mode. So if it's identified an issue with the for the performance. So I'm making changes for this right now. So we'll have to add a new resource control group. It will be called as a PLGA resource control group. So we'll have an option to enable PLGA group or disable, and also assign CPUs. Basically, it will work as work as a resource control group, but only it will be this group will be used for only PLGA. And there's in a system there can be only one PLGA group. It cannot be more than one. And still have to figure out a few things, whether we need to support a task-based association. So that is still had to be worked out. So I'm looking at that. That's all I have. Any questions on this one?
So that group is special because you name it PLZA?
Yeah, that's correct.
Okay.
The limits, limits for whatever you class limit set on that will be used for the kernel mode when an application moves to the kernel mode. So the limits will apply for that whatever class limits you're setting for the PLJ class. It will only apply for when it move the application move to the kernel mode. It can be useful for
So Fenghua said we needed to switch to James.
All right, that's good. Thanks.
I don't have any slides, so I should probably say something like opinions of my own, not my employer's. I don't want this to be a status update because that's boring. And instead, these are some ABI things that have been a bit tricky for MPAM, and they result in hardware features that aren't supported. I will skip everything about covering control formats, as Renee has covered that already. And I've got things fall into two categories of hardware features that can't be exposed. Things that are easy to add, and I'm aware the obvious thing might not be the best thing, and it might not work for everybody, and things that are, too short, things that are a little bit more invasive. And hardware exists for all of this. So the big obvious one is KVM support, which is currently ignored. All MPAM hardware can do this. Ben Horgan's looking at producing a series that does everything we think we need to be able to do, but there are lots of trade-offs. So likely there'll be a fair amount of debate about how much should or should not be visible. And the principal problem is there's some emulation work that needs to be done either by the VMM, something like QEMU, or KVM in the kernel. And typically neither project wants to carry that code. So I'd love to hear from any other architecture how they would, perhaps hypothetically, implement virtualization. So if we can, we come up with only one way that KVM needs to interact with res control, and maybe we decide it doesn't at all, and we do that all in user space. Another thing, so second thing on my list, that's come up on the list from Punit at Qualcomm has pointed out they've got platforms with monitors on the L2. That's easy to add, and that's probably the right thing to do. But adding new events makes me a bit nervous. And the reason I've seen a platform where the hardware people couldn't describe where the counters were. So one of the things in the back of my head is, where should we put the threshold of too hard to reason about for events or perhaps controls that people might want to add, but it's going to be very hard to express to user space what exactly that's doing. So I think any interface should be tied to stuff that is already described in ACPI, because then, well, it's not a new problem, or it's not a problem we're trying to solve. Third thing on my list, most MPAM platforms I've seen have monitors on the memory controller, not the L3, and res control names the events as if they're part of the L3, at least in the enum, and the domains come from the L3. So there's some fairly complex code in the MPAM driver that tries to spot when the topology is the same, and then it repaints the domain IDs to make them look like the L3. And that's also that existing software can use the existing interface. And Fenghua is going to talk about CPU-less memory nodes, which is the obvious kind of platform that suffers when you do this. I had something about minimum bandwidth controls. So currently the MPAM driver generates one format from the other, which means you just get a static offset of about 5%. And Renee already covered a better way of doing this. I think in the past I've mentioned the RMMU support, so a way of labeling traffic with a closet and an armid. I have some patches, and I think last time I brought this up, Tony thought there was a cleaner way of doing it. Currently that's all in CPU hot plug locked up hell. So even the old way I had of doing it doesn't work anymore. I mention it because I've not seen a good use case for managing cache structures inside the RMMU. Labeling traffic, yes, but cache structures within the hardware. So I think we should leave that alone unless somebody's got a use case that shows performance differences from doing that. Otherwise, almost at the bottom of my list, MPAM's got 3 types of control that we could add to schemata. And there are platforms with PRI, or PRI, which is an integer priority, bigger is better. CCAP, cache capacity, which is a fixed point fraction of the cache that you'd like to use, not the same as the bitmap that we currently have. And proportional stride, which is like a weight, how often you get a chunk of the bandwidth. And the reason for bringing this up, PRI and proportional stride are probably not going to be attached to the caches. So what should we use as the domain ID? Attaching controls to the things that ACPI already describes might work. But how do we tell user space that this is NUMA PRI and that one's L3 PRI if you've got 2 that are the same? So we don't get confused between platforms if people build different things. And I think it would be good to consider this for any new schema that are added. Today's edition, there was another talk earlier today about an MPAM platform with a different number of closet of the system cache. So it was something like 16 in the L3 and then 2 further out in the system. Currently, the driver just says you get 2. The MPAM's architecture, so the document from ARM that describes how it should work, has got a way of dealing with that, which is a feature called int part ID. And I intend to hide almost all of that in the MPAM driver. I don't think that's something we should expose to user space at all. I think it makes it very hard to think about control groups and monitor groups when you've got something that doesn't fit. And the plan is to drop controls that can't be aliased and reduce the scope to hide the effect. So the impact on that to res control would be a mount option to say how much aliasing you're doing. And as I'm going through a list, just for the sake of mentioning, I've not seen any platforms with the memory bandwidth bitmap that MPAM defines or the cache associativity controls. Please get in touch if you have a platform with either of those. Any questions, soft fruit, heckling? No? Okay. move on to the next. Oh,
Hold it.
Yeah, and I'm from Qualcomm, and probably we're in the same presentation of what we did in morning for the system cache for the MPAM. And is this some of the things you talked about? Is patches are out, or you are working on it, or I was not able to get that.
okay,
properly.
yeah, that's the status update I didn't give. So what I've been working on is feature parity with Intel Z on AMD parts. So it's only existing things in the interface that resctrl has that are being supported. I don't have any patches for the int part ID support, which I think is what you're going to find the most interesting. There's been some traffic on the mailing list. I know Dave Martin was looking at doing this, and I think there was somebody from Huawei who was looking at it as well. So there's some sort of thinking about how we might go about supporting that to try and keep it in the MPAM driver, keep it out of resctrl. But there's nothing, it's not the current thing that I'm trying to upstream, which is just feature parity.
You want to ask? No. The second question is that is there any of this you plan to move to MPAM FB, because some of this you need to do it on the MCU or
okay,
SCMI?
so those listening along at home, MPAM FB is a firmware interface to the MPAM hardware. So instead of using read-L, write-L to access registers, you send packets to a microcontroller, and it sends you an interrupt back when it's done. The plan is for all the controls to work in the same way. The difficulty will be the monitors. So the files in resctrl, that should work because they are always accessed from process context, so you can wait for that interrupt. If we do something like perf support, that's not going to work because you won't be able to wait for the interrupt in the contexts perf calls it in. So that's my warning for people doing MPAM FB. Otherwise, it should be transparent. So the accessors that go out to access the hardware registers, they just look up whether to send packets to a microcontroller or just access it directly. So you should get everything for free.
Thank you. We are very interested in FB part.
I didn't quite follow your comment about the IOMMU. Are we talking about MPAM SMMU v3
Yes.
support? And
Yep.
were you saying you had patches, they got tangled up in some CPU hot plug, and you're not sure they're worth doing at all? Is that what I heard?
So I think Tony's view was the way it was exposed as ABI wasn't particularly clean, and there's better ways of doing it. I have patches in the extras branch historically that did this. So they exposed something in the tasks file that named IOMMU groups by number, which is the existing structure Linux has, and let you assign them as if they were tasks moving around in the system, and you could, that would put them in a control group by closet or part ID. So labeling traffic coming from devices, I think we should support. I think if you've got an NVMe and a network card both trying to destroy the system bandwidth, you want to know which one's which. It's the structures in the IOMMU, so it's walk cache, it's TLB, and things like that. I think there are hardware controls for those, but I haven't seen any numbers to say somebody's done some experiments that says, oh, this is really worth supporting and exposing to user space. I suspect it's marginal, but there's no data.
Thank you.
Okay, talk about the CPU-less memory node. Basically, it's CSL memory, but ARM, we are doing the different things as x86. x86, just now, Tony and Babu talk about the CSL as belong to L3, so it's in the same node as CPU. But ARM has a different design. The CSL memory can be a standalone NUMA node. There are no L3, no CPU. So but it has a MPAM control on the node, so that makes the difference eventually. So when we discover this memory node, it's a NUMA node. So kernel understands that ACPI table, then understands that CSL memory as NUMA node. For the MPAM, it has another MPAM ACPI table to get the IOMMU address to access the MPAM registers for this NUMA node. access the MPAM, MBA and MBM registers on this node is through MMIO register. So since there are no CPU, no L3 on this NUMA node, so we cannot, the schemata right now is, if you check the spec, and just now Tony and Renee talk about that, it's always cache ID. When you control and monitor that memory bandwidth, it's always cache ID equal to a number, right? To allocate memory bandwidth. But we don't have the CPU on this. We don't have cache on this one. So we cannot identify this CPU-less node by the cache ID. So we need a NUMA ID to identify this. So you can see we're going to have the new line for allocation. I call it MBN. N means NUMA, right? The NUMA ID 0 equal to a bandwidth. NUMA ID 1 equal to another bandwidth. Here is not cache ID, right? So that's a difference. That's a new schemata format. For the monitoring, it's the same thing. Currently, we have the monitoring per L3, but we cannot, because we don't have L3 on this NUMA node, right? So I propose this new allocation, new monitoring for the CPU. I call it CPU-less, the last line. It's called CPU-less, followed by a NUMA ID. Then has the MBM total bytes. We don't have local bytes. There are no CPU, right? So that's another imbalance thing for this monitoring. We only can monitor total bytes. And it's based on the NUMA ID, not by the L3 ID. So that's another new change. So the discuss for this is, I propose these two changes. One is the schemata MBN, the NUMA ID equal to bandwidth for allocation. Another one is the monitoring. It's also based on the NUMA ID and only has the total bytes for the CPU-less node. So yeah, so basically the quickly brief explanation of the CPU-less, we have two changes. So if you have any idea, any question, we can discuss. I think I still have some time. Or we can discuss anything else, the previous presentation.
That would be very helpful for the RISC-V the RISC-V CBQRI specification, because we have the concept of bandwidth, and it's not tied to any sort of like specific thing. So it could just be a memory controller like this. So I didn't know where to put that because it's not a cache, right? So this would be quite helpful for the RISC-V spec as well.
Mm-hmm. Yeah. Yes, thank you. Yesterday I wanted to your presentation about the RISC-V risk control, right? Very helpful.
Yeah. Are there patches for this, or is it just kind of a concept right now?
Only concept. I'm doing tests right now.
Perhaps a different example then. I have patches in the extras branch which do this, but in a different way. So it adds a mount option that changes the MB domain IDs to the NUMA NID, and that's user space opting into this being different. It is just a different way of doing it. I suspect the good reason to add a new schema is if there are platforms with both, and if you wanted to try and control them individually. The way SNC looks, if people were to do that, they might need to have both.
Okay, yeah. Yeah, I didn't discuss this implementation with you. That's my personal implementation. So probably we can discuss this offline in details, yeah, after this. Yeah.
The other thing to note is adding anything like this means resctrl then has to go and take the memory hot plug lock as well for domains coming offline and offline, wherever it takes the CPU's hot plug lock.
Yeah. So you also need a mount option to turn on this, right?
For the approach I took, yes. For what you're proposing, you wouldn't, which is probably a good thing.
Okay. Yeah, for my proposed ways, I don't have the mount option. So automatically detect the CPU-less NUMA node, then add this new line for the allocation,
Yep.
yeah, and the monitoring.
The approach I took was thinking, if there's existing software trying to use this, and it only knows what MB is, and it's not particularly tied to the domain IDs, you could maybe say that it was safe for this. I don't know of any such software.
Yeah.
So we could just declare it as not existing.
Yeah, and also this proposal can mix the legacy CPU ID allocation based on per L3 allocation and also the CPU lines allocation. So they can do both in a mixed platform. Like some NUMA node has a CPU, some NUMA node doesn't have a CPU, right? So yeah, so probably it has two lines. One is for allocation for the legacy. One is allocation for CPU lines NUMA node. Yeah. Yeah.
Anybody else
If you
with any
have any
questions
other
on
question about the previous presentation, we can discuss now as well.
Otherwise, Fenghua are going to keep digging. So.
Yeah.
Yeah, I got a question for James or you. Yeah, so I'm asking that we got use cases for for the remote memory, which means that we can access the memory from one node to another node, and which is another machine. So we're adding another MMU to access the memory on another node. So I'm asking that what do we need to do to use that? This is a use case for the CPU-less NUMA node. But so shall we add in something in the memory control group or on the new added MMU or something like that?
I don't know if anybody's listening at home. I'm not sure I completely follow what the system looks like. If you're describing it to Linux as being NUMA nodes, then it's already creating structures in SysFS, and there's tools like LSMEM that will show those up as being NUMA nodes. I think you should do this. If it was something stranger, say if it were CXL was the reason you're doing this, it might be worth doing something different if it's not being described as NUMA nodes. I don't know enough about what you're describing.
Yes, it's so. Yeah, it's pretty similar to CXL. So I'm not sure. So how to do that in the CXL the use cases? Yeah.
Okay, if it does look like CXL, it might be worth looking at AMD's SMBA schema entry, because that might fit exactly what you need, in which case we should do that because it's not new.
Yeah, SMPA is very similar as this one, but they design as not a CPU-less NUMA node, right? So it's still CSL memory bound to L3, bound to a CPU node, basically. So even like a lot of different CSL memory device memory, so they all bound to some L3. So it's in the upstream kernel already for the risk control. So it's called the SMBA, right?
Okay.
So Babu knows this more than me.
Thanks.
Yeah. But here we have different implementation. The CSL doesn't belong to any L3, doesn't belong to any CPU node, right?
Yeah.
So it's standalone.
Just a quick question on that. Where does the throttling occur for this memory bandwidth allocation? And then the monitoring to be able to understand what the limits are, and then the throttling.
For which system, sorry?
These systems that Fenghua is talking about now. The nodeless ones.
What's the question?
CPU-less, sorry.
Yeah, so you are saying about the IOMMU, who control this memory bandwidth on this CPU-less node?
Yes, so a user may use this schemata to set some bandwidth limits associated with that NUMA node. So I'm curious where that monitoring is done and that throttling is done. Where in the system?
Yeah, so because this is MMIO address, the register, right? So basically, the for the x86, we have the per L3 control. So it's on one CPU node, right? But this CSL memory node also has MPAM related control registers. Any CPU can access those MMIO registers. So any CPU actually can control this MPAM on the CPU-less node.
Oh, no, I mean the memory bandwidth itself. So when something runs on a CPU and it maybe needs to be throttled, where does that throttling happen? Is it, sometimes it just happens like right after the L3 miss, it understands that it can't go further. And I think that's why it's often associated with the L3. So I'm wondering the system, when it enforces these bandwidth limits, where are these bandwidth limits enforced on the system?
Yeah, go ahead.
I can describe how ARM systems typically do this. I don't know how Fenghua's platform does this. So the interconnect standard for ARM systems has a signal called CBusy, and it uses that to put back pressure up into the system to say slow down. So I think you're describing having the MMIO registers in the memory controller. So it would be the memory controller saying slow down for a particular part ID or clause ID. And that would then go back to wherever the requests were coming from, and it should track that by part ID or clause ID. So it could be the L3 that's slowing down, it could be the CPUs. This stuff isn't defined by the MPAM architecture, so it can change, but that's what I've seen from the interconnect standard. Does that answer the question?
Yes, I'm curious about the scope of that throttling. So if the scope is being throttled at the L3, for example, then it may be similar to the other architectures.
I think that can definitely happen, and I think it can also, if you're, I think it can also get back to the CPUs. So I've seen some trick they had for resetting that when changing tasks. So it definitely gets back to the CPU as well. I don't know an awful lot about how this works. It's a hardware design kind of thing.
Thank you.
Yeah, I want to say like this is the remote, right? So it's not local. So any CPU access to this NUMA node, CSL NUMA node, is always remote. So probably that's. Does that answer your question? So it's not like belong to L3, because before I work on x86, this memory always goes through the L3 between, we do the monitoring allocation between the L3 and the memory, right? That path, we do the allocation monitoring. But here, the ARM looks like different. It do like this one, not between L3 and the memory, basically. At least this is remote, right? It's not local. Yeah, is that okay or?
Yes, thank you.
Yeah, any other question? Actually, I have a question for Babu, but I'm not sure you can speak or not. But just now you mentioned that zero, that one is, yeah, this one, privilege level 0 association, right? So whenever it go from user to kernel, from kernel to user, it switch class ID and RMID. Is that the idea about this?
Yes, that's correct. Yeah, that's correct.
Yeah, what's the overhead to do this switch? Because for x86, it's access MSR. The cost is very high, right? Before when we designed this with Tony and Renee, actually we consider this, but overhead is so high. Go enter and exit from the kernel when we switch class ID, RMID, we cannot stand that overhead. So you have
Yeah, yeah. This is done at a hardware level. So basically, the OS doesn't switch it. I mean, it's automatic done at the hardware level. So you basically set up PLZA class, and you set up the limits on the class, and hardware automatically switches it. So we don't do at context switch, but if you have to support task-based association, then we'll have to do when task moves from one CPU to another CPU, then there is a cost for that. So I'm working on that. But if there is just a CPU, there is no, we don't have to write any MSR. It is taken care by the hardware automatically.
Yeah.
Just to comment, all MPAM hardware can do this as well. And similarly, the cost is free because you don't need to context switch the register. You just set it up in advance.
Yeah, I think it's free. It's only 1 to 2 cycles. I mirror that. But I mirror the x86, it write to PQR, associate MSR,
Yeah, so
a few hundred cycles.
If you
so
have
that's a
one
big difference. Yeah. I'm not sure AMD. Yeah. Yeah, here it's not a context switch, right? It's just changes the PQR, associate MSR. Between the user and the kernel. So if you do that frequently, I'm not sure. It's.
I think they're not rewriting the MSR. They're just saying the value that you use depends on the currently ring level. So if you're in ring 3, you use the value in PQR ASOC. And if you're in ring 0, you use the PLZA value.
Correct. Yeah, that's correct.
Oh, okay, I see.
But the task-based association, we need to write, change the MSR. So that part I'm still not very sure yet, so I cannot comment on that. But if there is, it is set up automatically in the one time, right? It's only one time setup, most part.
Okay, I see. Thank you.
It seems the interface among L3 cache ID, the interface is unsuitable for because ARM hardware counts the transaction passing through MSC. So the interface is unsuitable for traditional NUMA node.
So which slide? Which slide are you talking about?
27.
Okay. Oh, okay. Yeah.
Interface among L3 cache ID. This interface is unsuitable for traditional NUMA.
Yes. Yeah. Because traditional is monitor, it's monitor memory bandwidth, but it's memory bandwidth monitor is between L3 and the memory. So it's memory belong to L3 basically, right? So we just use the cache ID, L3 cache ID, and monitor that cache ID to identify which part we monitor, right? So it's per L3. But CPU-less, they're not L3. So that's why I said, okay, we need a different name. Yeah.
Okay.
Yeah. Thank you. Yeah. Any other question? Yeah. By the way, for the RISC-V, do you have any other new features like need like a risk control change?
Well, they're very abstract in nature, right? So we just have abilities to control capacity and bandwidth and monitor capacity and bandwidth. So those are pretty abstract in terms of what they could be. I mean, the only implementations I'm aware of are doing it for cache controller, so like the capacity in a cache, or for a memory controller controlling the bandwidth. So I'm not seeing any other like resources being controlled, but like, you know, when we were working on the spec, we discussed it could be things like interconnects or TLBs, but like I haven't seen anyone doing anything with that yet. So, but the biggest challenge with doing the implementation for the RISC-V spec was that, yeah, we have the idea of like a memory controller could be handling the bandwidth, and it is unrelated to cache. So this is quite helpful what you presented, I think, in that regard. And then I guess we'll see what people do, because the spec is very generic in terms of what you could do with it. So it could present other interesting challenges, but the memory controller is the biggest one, I think, right now.
Okay, yeah. So do you expect like any risk control interface change when you port to RISC-V?
Well, I think just in terms of what resource would fit the memory controller. So I think what you've described, it would be good. In terms of the cache, I think the cache is pretty much, we don't have the other, it's just like a bit mask, that's all it is. So I should correct myself. We have a block mask, which is like a bit mask, but then we also have something called C units, which is capacity units. So if the block mask is describing like the cacheways, then the C units, the capacity units, would be like the number of cache lines. So let's say you only have a few number of like resource IDs, then you could have additional entries where it'd be like the same resource ID, but you would change like the number of capacity units, aka like cache lines that like different access types could use. So it allows you to basically differentiate further beyond just like the capacity blocks, which could be cacheways, versus like a more granular these capacity units, which would be something like a cache line.
Yeah.
So that's probably a little bit of a quirk that you know, would present additional issues of how to represent that as a resource in the schemata, because it wouldn't just be like the bit mask, it would also be like the bit mask for like the less granular, and then the more specific would be like how many cache lines can you use within each way. So there is also that in the specification. So that would, yeah, pose a challenge as to how to represent that in the schemata. But I think the implementations I'm aware of right now is just using the like bitmap to like the bit mask to represent like the cacheways.
Okay, yeah, thank you.
And then I guess for bandwidth, the other thing is there's the idea, like there's reserved bandwidth, which is similar to like MB, like how much, like what sort of, how much of the reserved bandwidth can you allocate? But then there's also the idea of a weight associated with the unreserved bandwidth. So for the bandwidth that's not reserved for specific resource IDs, then you can also set for each resource ID, like how much of the unreserved bandwidth can it use? And it's sort of a sum of different weights. So that would also be another thing that we had to think about how that would be described in the schemata. So there's a few additional like quirky things like that.
Yeah. Yeah. Okay. Yeah. Thank you. Any other questions?
I just have a quick comment for, I think if I understood James correctly, there was a need to express more events. Please take a look at some recent changes in support of package scope events, in support of Intel's application energy telemetry. It started to separate the meaning of events. The ID is not associated with event IDs on the hardware anymore. So maybe take a look at that. That separation is it's not so cleanly associated anymore. It's starting to separate, and we may just keep moving in to support those L2 events.
Okay, thanks. That comes from my comment of sticking it with the L3 to try and keep exactly as it was at the time. And if it's changing, that's probably good and easy for platforms. Thanks.
Yeah, I think next group is coming, so we are running out of time. Yeah, thank you very much. Yeah, okay. Yeah, thank you.